Well, good evening, everyone. Welcome to this talk by Andrew Reiter on distributed RF spectrum analysis. I think everyone's lately been buying cheap SDR sticks and playing with them, and Andrew has been doing more with them.
All right, thank you. Like you said, my name is Andrew Reiter. I come from US, and I'm very happy and glad that I was invited to be able to come here and speak in front of all of you. It's a pretty amazing place and really amazing conference with a lot of amazing, very friendly people who are doing a lot more intense work than I have, but hopefully this will be very interesting to you all. First off, there's entirely too much content for us to cover in one half-hour session here. You know, some of this content, as you know, can be given for full-length semester courses at a university. So, like such as antenna theory, things of that nature. So don't worry about feeling confused. Just sort of get what I'm trying to get, the key terms that I'm throwing across, get some of the ideas in your head that I'm trying to express, and then afterwards, review the slides, do some further searches on the internet, use the references, things of that nature, and then hopefully, you know, you can build your own array. Lastly, a while ago, a friend and I, we created this Radio Punks mailing list, sort of named after the cypher punks, and it hasn't gained much ground, but that's really due to lack of trying to push it. So there, I'm pushing it. The last slide or two has the link. So as you all know, in recent times, there's been a great deal of increase in RF traffic. We can particularly see this in the United States because of the FCC's working to reorganize the frequency allocation table and basically making channels less wide because of the accuracy of the hardware and the increase in numbers of people using the RF spectrum. Also, the cost reduction in hardware has, you know, dropped a ton. So there's a great deal more devices being developed by manufacturers, companies, and that such. And also, there's people like Mike Osman and the people that made Blade RF that are doing, you know, non-regulated devices that can transmit. So it's a challenge for us, in my opinion, that we should be wanting to know what is being transmitted over the air. And so should what's in the air also be in the air, if that makes any sense. It's our duty to sort of first understand channel frequency occupancy and probability distributions related to channels in the spectrum and how, you know, which protocols are using them, how often are devices using those spaces in the spectrum, things of that nature. And so that we can be aware sort of the existence of signal. And then we can work towards understanding the signals. You know, the governments are listening, and so should we. So I feel it's my duty to sort of talk about the array that I've built using RTL SDR devices, so everybody else can build their own if they desire, so that we can, as a group, increase our knowledge as to the existence of signals throughout the spectrum. And then from there, hopefully work towards breaking them down. So hopefully this will get you motivated to build an array and then participate in a future project that I'm working on, which we sort of link everybody's arrays together and get a feeling for the worldwide RF spectrum sense. More of an innocent motivation for my building the array is I effectively live in the woods of Western Massachusetts in the hills. And so I go for hikes a lot. And 2 miles into the woods or so, I come across this crazy device. I'm like, what the heck? It's got, you know, sat antenna there, and the big guy right here, UHF sat antenna, and then also had a cellular antenna, and it was basically used for measuring the water tables in the hill areas. And so it really, you know, made me kind of think, you know, oh, wait, duh, there are, you know, places transmitting even though I can't see an antenna. And so I was like, okay, you know what is actually out there in the spectrum around me? I live in the woods, what can I capture? What am I not seeing? But first, before I go into some details, I just want to be clear. The RF scanning array, it's basically just a group of RF receiving devices, and their whole purpose is discovering signals in the RF spectrum. This is just power analysis. We're just, FFTing IQ data and looking at the power values at different frequencies. And we're looking at the noise floor versus spikes. Different from this is then, demodulation and analyzing the actual protocols that are going over the spectrum and identification of those protocols. But as I've alluded just before, recognition of the existence of a signal is the first step to actually moving forward. The basic array components that you are maybe all aware of, or not, you're going to need basically 5 things. Software controllable RF receiving capable device. This is something that will do analog to digital conversion so you can get IQ data. What I'm going to show is that I use RTL SDRs. SDR might be a misnomer for these RTL devices as they're more just controlled as opposed to software-defined radio. Next, you'll obviously need antennas in order to go out there and reach out into the air and grab what's there. You'll need the cabling and adapters for antenna and to the RF receivers. Sometimes this is just sort of overlooked, not the cabling, obviously, but just the fact that when you're building out an array, you're going to need a lot of cable. You're going to need a lot of different adapters, and it's sometimes a pain in the butt because not everybody always has them in stock, that kind of thing. And then obviously a computer able to control the RF receiving device and then process any IQ data that you get. But this sort of naturally leads into this sort of component choice problem. And I just wanted to introduce it early on because it's fairly important. Most receiving devices have a fairly limited range in terms of frequency width, bandwidth. For example, if you look at the Osman's HackRF, you're maxing out at 20 megs of bandwidth there, but you're not even going to get that because of the limitations on the USB bus. And so you kind of need to be worried about the device capabilities that you're purchasing. Further, antennas also have sort of frequency range issues. Due to the nature of how RF is transmitted in the spectrum, you will have certain antennas that are purposed for UHF, for VHF. Some work well for both. Some are intended for a small frequency range but get high gain. Some are intended for a wider frequency range but aren't that receptive to the signals that are out there. Further, when you're building out this array, you're also going to be acquiring a lot of raw data. And so if you're planning on storing it, you better either have a lot of hard drive space or just be ready to lose the historical data. So that's an option that's a choice you'll have to make. And further, well, this choice is made for you. Virtual machines are just really not an option for this. The I/O is just too intense. So there's a lot to consider here. So the idea is that I suggest to start small, start cheap. Start with the UHF and start with VHF and the lower ends of the UHF spectrum. Basically, use RTL SDRs that'll get you 50 megahertz to 22 megahertz, or 2.2 gigahertz. And you'll be able to get all the cabling, the adapters, and all those things fairly cheap. So I want to share with you sort of the receiving hardware that I've used. As I mentioned, I've used the variety of the Realtek RTL 2832U based USB sticks. Most of the sticks that you find will have this chip, but then you have the tuner chip that goes along with it. And the best tuner chip out there for these is basically the Alonix 4000s. And this will basically get you 50 megahertz to 2.2 gigahertz with some gaps at around 1100 to 1300 in that range. I also have been using these Raphael Micro tuners, and those aren't as good. They get a little bit lower. They get down to 30 megahertz, something like that. But there is a limitation. I believe the upper bound is about 1700 megahertz. So as you can see there, already I'm kind of limited. I chose these. I'm doing 50 to 2200 or 30 to 1700. And yeah. And also in theory, these should support a bandwidth of 3.2 meg. But really, if you're doing that, you're going to actually have data loss. And so it's basically recommended to drop down. I know people have seen some numbers, 2.6, 2.4. I've basically just been doing my setup with just 2 megahertz, just make it a power of 2. And these are some of the devices that I have actually in my array. The ones on the outside are the ones with the Lonix tuners, and they have PAL connectors. The one in the middle here is a newer one that I haven't used as much. This is the one with the Raphael tuner chip on it. And the connector actually for the antenna is an MCX connector. It's quite small, but it's a lot more strong than the PAL connector. With the weight of the cabling, I've frequently snapped these off. And the nice thing is that, I don't know how the scale is here, but it's like, the size of the end of my pinky. So soldering something like that back on is quite easy compared to, a lot of the SMD stuff that's going on today. So that's really not a big deal. So those are the actual receiving units that I'm using. Now we go to some cabling and adapters and that kind of thing. For basically everything, I'm using RG6 coax cabling. 75 ohm impedance, and it basically works great for all the UHF and VHF analysis that I'm doing currently. The adapters that you're going to have to be worrying about, typically for the PAL guys on the left and the right, you're going to most likely need F-type to PAL. And for the guy in the middle here, typically I put SMA to MCX, but really there's F-type to MCX, all sorts to MCX. I think I just made a typo. Further, another type of adapter and plug that you're going to need is typically for your antennas. And I wanted to point this out because it's commonly used. These are UHF plug or socket and the actual plug right here. And this is a PL259 plug that actually converts to F-type. But typically, when you're talking about F-type and SMA and all those things, you have female or male. Well, actually, in this realm, you're actually talking about SO239 is the female piece, and PL259 is the male piece. This is like the weird one in the whole bunch. And as I said before, when you have all of your hardware together and you're like trying to assemble your kit and you're missing one or two of these adapters, it is a pain. It is a real pain in the butt. I've experienced it, and I've had to wait like a week or so because nobody near me will sell any of this hardware. And so I always have to order on eBay or from some specific dealers down in the south of the US where apparently there's a lot more people using ham radios and things of that nature. And the key is to buy a bunch. Always have extra. Always have a box of them, be able to hand them out to friends, that kind of thing. And I also say to look, when you're looking, if you use eBay to order, beware of anybody selling from China. And I know that's kind of like a blanket statement, but in all honesty, I've had to wait 3 to 4 weeks at a time just to clear customs, just to get an adapter, which is just totally ridiculous. There's no harm in that. Let's talk about antennas a little bit more. Basically, depending on your needs, location, and where you're basing your array really determines what antennas you might want to get. As I mentioned before, they're very specific in terms of the frequency ranges and the directionality of them. Primarily, I use omnidirectional discone antennas. This is like the one on the left right here. Primary reason is because of the omnidirectional nature of it. I kind of live in the woods. I don't really know exactly where I'm looking for. I know where there are some big towers that are transmitting higher power, but I don't know exactly what's going on all the way around me. And so I don't want to dedicate some Yagi antenna or log periodic antenna on the right here that are directional so that I'm limiting my view. My one problem here is that the omnidirectional, I'm losing some power. I'm not getting all of the power out of the spectrum as I could, I guess so to say. Furthermore, instead of buying an antenna such as those, you can build one easily. This is very easy to do. You just need some pine, some screws, coat hangers, things of that nature, and you can do this. These guys, I'm not going to show this video now, but I wanted it in the slides. The BBC Ottawa folks did a great little 5-minute video on building a UHF VHF HD TV receiver for some of the new digital over-the-air stuff. And it's like this big, takes 5 minutes to build. It's simple. Furthermore, when you're building out your antennas, clearly mounting is a big issue. Trees, buildings, they all block signals. They can refract signals. And so the idea is to get your antenna as high as possible and with clear lines of sight around as possible. If you're unable to do this, one thing that I've been doing, because I rent the place that I live in, is that I've just been taking PVC and basically building large mounts out of them and then using other shelving and basically building up and up. It's total hack job. I'll show you pictures in a few minutes. But it works, and so it's worth mentioning. Further, I have a reference on the last slide and the references slide about rules of thumb in terms of height and distance to the transmitting tower and sort of knowing what you should get out of a signal if you have an antenna at a certain height with a relatively clear line of sight, those kinds of things, and it's worth reading. Last two things, grounding your antennas. This is important. You're going to fry your electronics if you don't. I'm sure you will. And probably the next most important thing is labeling. When you are building out your array and you have a bunch of antennas and then multiplexed out to a bunch of wires, you're going to need to know which wire went to what antenna if there ever was an issue. Did the wind knock something down or whatever? You're going to want to know which machine that was going towards or which antenna that was going to. So this is sort of an example of just using the omnidirectional head mount and how easy it is to just put it onto a PVC pipe. It just fits quite nicely. This is like a 1 1/4 inch. I know that's different here. Sorry for the measurement changes. And it just fits on right nice. And boom. Well, this picture isn't so great in this. But you can see this sort of wire shelf thing and then these 5-foot antennas that go up. Admittedly, this is not the best setup, right? I live on a big hill though, and it sort of really does open up. And so this actually works. I get pretty clear, accurate signal, and there isn't much interference from those trees. Mostly probably because they're thin fir trees and that kind of thing like that. And some of them are almost dead and falling on the neighbor's house, so that probably has something to do with it as well. Further, since I have this sort of way out in the yard and the cable's running down, this is more of an up-close picture, you can see where I've done labeling. It's very simple. All I did was duct tape, 1, 2 duct tape, 3 duct tape. Super simple. But what you see is that when you bring the cabling back to the house at the grounding site, which is also another hack job, I have labeling again so that I know exactly which cable came from way out in the yard all the way directly to right where I'm grounding. And so at this point, you kind of have your antennas out there and you're wiring them into your house. And it's important to think about your ability to maximize the antenna usage. What I mean by this is, are you going to be able to mount 10 antennas on your roof or on your landlord's roof? Probably not. or probably that's too much of a headache or too costly to actually purchase those antennas. Maybe you don't want to build all of them, that kind of thing. So really what you're most likely going to end up doing is buying a multiplexer. And this basically takes an input signal and splits it out into n output signals. And typically when you're thinking about cost, these multiplexers, as you go up past the gigahertz range, they're going to increase in cost a great deal. So that's something to consider when you're trying to choose the frequency and the frequency blocks that you're trying to scan and monitor. And further with multiplexers, it's really worth knowing this trade-off. Non-amplified multiplexers will reduce the signal and typically depends on the range that the multiplexer supports. And when you buy it, it'll stay right on there. And you just have to take that into account when you're doing the power analysis. Also, you can just do amplified multiplexers. This is sort of an example of one here where there's a power in, and that actually goes to a 12-volt adapter. And it's good in my opinion, but the issue is that it's a little bit noisy. You're basically just adding gain to the system, and there's added noise. And so here's sort of the mess, and I even go further labeling at the multiplexer level so that I know exactly where in this whole chaotic mess antenna came in, where did it go, which node has the various outputs signals from that antenna. And lastly, sort of just to give you a picture, this is the 12 node or 12 SDR array that I have going. Now, 1, 2, 3, 4, 4, 4. As you can see, most of them are the PAL type that I mentioned before, and most of them are sort of sagging downwards, and yeah. I guess there's nothing much I can do with that. I've sort of put some like little stints in there at times, but it didn't really help very much. Those just continue to bend. So this is kind of a brief aside. Don't buy these. When I was first messing around and I was just like, oh, I have one dongle, I have two dongles. Let's do the tetra dongle and maybe an octa dongle. And these just suck. They will, like I was just getting spurious errors. You know, they were partially in libUSB, some in libc, but it was totally the cable's fault, I'm sure of it. So lastly, and I know we're kind of getting time and the Greenwald talk is coming up, there's a very important point to be made is that, well, now that we have all this hardware here, we need to be able to do something with it. So we need to discuss the software side. It's sort of my opinion that to do this as a distributed approach. There's a lot going on in this system. And the positives of sort of spreading this out include, you know, being able to do the RXing I/O on all the different machines, be able to do the CPU intensive Fourier transform, possibly on different machines. Also the data storage I/O and just, you know, doing all the writes for that. It helps to just push that out. However, the negatives are the fact that you're going to have to buy extra networking gear unless you just have some around. You're going to have machine costs, the power. If you don't have some extra machines just laying around, then you know that's a problem. You need to buy them. And just in general, the complexity increases anytime you add systems to a network. Briefly, the designs I quickly tried were a sort of master-slave setup using the Pi RTL SDR Python bindings driving the USB dongles. Master-slave setup where each dongle is associated with an RTL TCP process, which is part of the RTL SDR Osmo Com guys. They push that out. And then using GNU Radio on the master to do a workflow. And then lastly, this is the setup that actually ended up using the most and I have enjoyed using the most. And what I sort of recommend or would hope people would work towards, I guess, is that I have some custom C code that is heavily based on the Osmo Com guys stuff. Fully admit that, you know, all the licensing stuff goes to them. That's great. and I will discuss that now. We can sort of skip this. So with the first example that I showed, all of the slave nodes, which actually have the RTL, SDR devices connected to the antennas, will then recapture RF data at a time. They'll capture some chunk of sample size, and then they'll just push that IQ data back to the master. They will just keep reading, pushing, reading, pushing, reading, pushing, reading, pushing. And the master the whole time has to read off the wire, do something with it. And most of the time what it's doing is FFTs. So basically you're doing an FFT per packet, per capture, per slave on one machine, and then add the network IO and disk IO, and that machine's basically, it's starting to eat the dust. Similar kind of goes with the second one that I mentioned just before, which is where we have RTL TCP running on all the different dongles on all the different slave nodes. It sort of matches the topology on the right. It's just using RTL TCP instead of some pi RTL SDR bindings that send over the IQ data. This way, it's using the direct C code, using lib RTL SDR directly, and sort of removes that overhead. The different thing here that also by using RTL TCP that I get is the fact that I can then use the GNU Radio Companion and build my own workflows, and there's some real flexibility in being able to do that. The primary one that I was doing for the power analysis was I was using the RTL TCP sources, pass those into these FFT blocks, and then I wrote my own GNU Radio sync that would aggregate the FFT data and do some just analysis, just comparing the values and things like that. Furthermore, this also, because of the previous example, will also crush your one machine because it's doing a lot of the heavy lifting. So sort of what I decided to come up with is this monster diagram in which actually reflects the legitimate setup that I just showed before that I have running. I have one master node, I have a database, 3 slaves, and on each of the slaves there's 4 RTL dongles on them connected to the antennas via multiplexers. The design goal was to push all the FFT processing back to the slaves, and then just transmit the power data back to the database and store it in the database, and then let the master query that database and find out about what the nodes had found. Another design goal is to increase the functionality away from just being able to do the FFT and the power analysis to being able to say, okay, I see a spike, let's raw capture. So, I've added that support to it. Also, similarly, if we see a spike at some frequency, boom, start up RTL TCP and then choose a GNU Radio script. Maybe it's just FM and you can just listen to it. Maybe it's something else and you want to do further decoding like POXAG or ADSB, things of that nature. So each slave node runs this thing that I call MegaRMON, which is Mega Array Monitor. And as I said, it just captures the RF data, does the FFT, and inserts the powers in the database. Slave nodes again. The database node is there just to store information about all the nodes. Physical location, longitude, latitude, longitude, things of that nature. Actual device index on the machine. Its current status as to whether it's scanning or not. Also, it stores the frequency block distribution, how each of the slaves choose which frequencies they're scanning. And all this is configured ahead of time. I admit I'm running out of time, so let's see, I'll show you a couple things here. The primary things, I have a GUI that I've sort of developed. And what this is showing here is the power versus frequency from 50 megahertz all the way to 900 megahertz, which is pretty cool considering that this is just RTL SDR devices is doing 2 megs at a time. That's a pretty wide range. And however, note this bottom part here. You can sort of see the 3 chunks, right? That has to do with some cabling, some bad antennas, things of that nature. Really, that's just fixed. Let's see if I have a picture here quick. Yeah, here, I've fixed that essentially using some manual gain options and things of that nature to level out the signals. And the purpose of that is, the purpose of my wanting to have that a noise floor that's consistent is the fact that I have this thing that I call a power breakers list. I can set a threshold value, which is just a decibel value, and click refresh, and it'll give me the list of all the frequencies that broke that threshold. And it's very helpful in just kind of knowing over the last N minutes what's been really spiking, what's been in use. And yeah, all right. So further description about my array. Like I said, it's scanning 50 megahertz to 900 megahertz, 4 RTL SDRs per node, 12 times 2 megahertz. And then 3 omnidirectional UHF, VHF discount antennas, 3 4-way amplified multiplexers. I've had this running 7 days at a time. Only reasons to take it down is to update code, things of that nature, no memory leaks. It just runs, it just goes, and it sucks power out of my house. But it's fun. Again, I apologize, but I'm gonna have to urge you to kind of go back and look at some of these slides to just sort of realize how I do the breakdowns in the range, how I associate them to each of the device nodes and how they scan. Further, I also have some example videos that are a bit too long right at this point in time for me to share that sort of describe, although I thought this was kind of neat.
Will your presentation be available?
Yes. Yes. So this, I found like,
Sorry,
yes, ask a question.
I know that the keynote is starting now.
Yes.
Some people would want to.
Yes.
But I think for some of us, or a lot of us, they want to have that info. I don't know, the room is not booked for the next,
The room is available for the next half hour or something still. So, he's asking if there's still time here to finish that.
So I think it's easier for people who would like to see more data, more information.
Sure.
They just click here, and if people want to leave now for keynote.
Is that okay with you guys?
Yeah. We
Okay, let's just
we'll continue for
recess
if you
for a
wanna leave
moment
for the
and
keynote.
let those leave who want to leave. Thanks. Appreciate it. I'm sure the Greenwald one is good anyway.
Couple moments, we're still sorting video again.
Aha, we're back. I appreciate that you guys are all interested. Guys is a bad term. I apologize. I know there's a lot of uproar about that. So to skip back to where I was discussing, I was just mentioning the different nodes that I have. I mentioned the slave nodes to death. The database node, there's not too much exciting here. Just know that there's a couple key things. There's configuration and the frequency block distribution and the node information so that we actually know which machines have what nodes and then assigning frequencies to those nodes. This is a step that's a little bit weird to be doing command control by or command dissemination via database table, but I already had the database up and running, so I was just like, let me just make a commands table and then just insert it to it, and then they can query it, and if they get a command, boom, they can continue going. And basically, the commands are there for just starting the scan, stopping the scan, starting the RTL TCP stream, stopping that, doing writes, raw IQ writes to file, that kind of thing. So it just gives you a little bit more flexibility than other than just receiving these power values and being able to do analysis on that. So this master node, as I said, its whole thing is to control the slave nodes via the DB. And all this is kind of a little bit repetitive, but the only direct interaction with the slave nodes that it will ever have is if you optionally decide to say, hey, I want to do RTL TCP and run a flow graph, well then obviously your master node is then physically connecting to that TCP port on that slave node machine, and so then, boom, you're connected with it. Also, the way I do the raw file captures is I want to aggregate them from various nodes, and so really what I do is I just have NFS mounts that mount onto the slave nodes. I write locally the IQ data to a file on disk, but then I move it over to the NFS mount after the capture's done, all that kind of jazz. So those are the kind of two real direct interactions between the master and the slaves. Everything else is done via the database, which I still don't know how I feel about that. I'm so used to just having protocols embedded, or commands embedded in a protocol somehow. But this is just another form of protocol. Anyway, so the master GUI that I've kind of developed has the power over spectrum graph. This will plot frequency on the x-axis, power on the y-axis, and is a dynamically configured view range. You can basically set min-max so that if you wanted to hone in just on the FM band and look at 85 FM to 110 FM or something like that, you can get just that chunk and see it in much more detail. Also, that you'll see is a power over time graph. Basically, the thing is you choose a specific frequency, and it'll give you the power levels over recent time. This is sort of useful to see, wait, was that just some spurious spike that who knows what the heck that was? Or is this a commonly used frequency by people? Which usually over time you can sort of tell. And obviously both refresh with time. And then lastly is this power thresh breakers, which sort of strong signal analysis might be a strong phrase for it. But the idea is here, is just, as you'll see, just give you a list of frequencies that are showing strong signals, and the ability to kind of, double click on them and then have it automatically pop up in the power versus time graph, or just double click it and then say run, and it'll automatically hook up to an RTL TCP or a node running RTL TCP, and then do the FM demodulation. And so it kind of just, the whole idea of this GUI is to make the flexibility that I'm aiming for in this array to actually be user-friendly, which hopefully is probably going to be a more long-term goal than anything. So I briefly mentioned this, but I want to put up the slide again, just so that it's clear what I have here. I essentially have 4 machines, 3 slave nodes, 1 master, and then I share the master with the DB. Scanning 50 to 900 megahertz, et cetera, et cetera. All the node hardware is pretty much things I found around my house. My master is just a 64-bit laptop with 8 gig of RAM, and it's fine. I have an external hard drive over USB 2.0, and it works fine. The slaves are a mixer of 32-bit and 64-bit machines, no more than 2 gig of RAM in each. And really the process size never gets over like 20, I have to verify that, by like 22K or something like that. It's really small. And they're all running Linux, and like I just said, the idea is to just use the machines that you have laying around in your house. I'm sure all of us have either machines that we've gone through and they're just junk now, and well, they can be repurposed for this type of work. So this is sort of repetitive. Break these 50 to 900 down into 3 chunks. These 3 chunks are assigned to each of the antennas that I have, and then I break each of those 3 chunks down into 4 subblocks that are assigned to each of the nodes, each of the dongles. So it sort of looks like this. You have the full block, and then you break it into 3 based upon the antenna, and then you break a small chunk of that one into RTL's index 0, 1, 2, 3. So I kind of do a uniform breakup of the spectrum to the resources I have available. So you're going to have to excuse sort of the video in some senses, because I was trying to do this with a cell phone and like type at the same time. So hopefully. There's some cuts here to shorten time up. So let me start that from the beginning. So I see, so I'm just sorting the frequencies that are broken this dB threshold. I see that I grabbed 92.2 megahertz, just about. This is jumping around. But I want to actually then listen to it. So what I did is I go to this menu that I have, and I was able to say node 01-3, stop scanning, but then start a TCP. Now, obviously, this is stuff you want to automate, but this is all for that. So now, okay, node 013 is now streaming. So pops up in my little list, double click, it already remembers the fact that we had double clicked the frequency before. And then it just runs the GNU radio wideband FM demodulator. And I thought this was kind of neat because this was totally random. I thought that was kind of neat because it was totally random. I was just trying to film something for this, and I was like, all right, I'm keeping it. Let's see here. This might give a little bit better of a demo, but. So here you can see I've changed some of the interface. I have a last n minutes thing here now so that I can sort of say, hey, I want to expand the breakers list in time. So let's see. Choose 157 randomly, and I see the power analysis versus time. Sorry. It'll focus, I swear. There we go. So you can see it's a pretty strong, steady signal, a couple drops here and there. So I decided to do the FM demod on that to see what would happen. Right? So the idea of those two videos was just to give, I know they were not very pretty, but just to give an idea as to sort of the flexibility that I'm going for. The ability to see the spectrum and then pick out certain parts of the spectrum, look at it over time, and then possibly doing some real-time analysis or possibly capturing that data to a file and doing post-processing. So there's still some work to be done to make that all very clean, but the basic building blocks are there, and you just need to link up a few methods. So that's decent. One thing on performance, which I think I skipped the end of that last video, which actually might be interesting to show. I didn't include it. The point was that you will see on the power graph, the spectrum graph, that one of the nodes will be taken out of use when it's actually being used for RTL TCP streaming. And so there's actually like that chunk that has no signals recently available to it. So it's like you have all this signal, like noise floor signal, blah, 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 but then it just drops off and then picks back up. And that's a weakness. Something that could be done is reconfiguring surrounding nodes to try to pick up the slack. Some very wimpy statistics that I've kind of generated. Okay. Basically this is just doing sort of a select queries on the database just to see in general what I've gotten. And it's basically one power sample per frequency every 3 seconds. And then the database with insertion of this frequency values over the entire 50 to 900 megahertz spectrum, I'm increasing 1 gig at a time, or a day, or blah, 1 gig per hour. And these are just sort of rough statistics, and there's definitely more that should be done in terms of analyzing how one uses RTL TCP or writing out to a file and how that impacts the number of samples put in per second, that kind of thing. So my next steps for this array, and I know I'm wrapping it up here, is basically, like I mentioned, work in progress in the GUI. There's a few things that I just want to clean up and then hook some of these other manual pieces together so that instead of me clicking to stop from scanning, starting the TCP stream, clicking that I want the FM, just do it. You know, that should all just be hidden. And it's capable, it's just method calls and it's all there. If you do want the code, come talk to me. I will give it out. But admittedly, there's some things I'd like to update before I release it. My plan is to release this so that people can take it and modify it, enhance it, and make it better. I'm sure they can do that. Additionally to the array, I'm planning to add 2 more antennas. And these are log periodic antennas that I'm sort of hackfully building together. This you can buy for like $30 on eBay or from a lot of retailers. And this thing can work fine on its own, and you sort of point it in the direction that you want it to go. And it'll do 900 megahertz to 20 or 2.6 gigahertz, as you can clearly see here. But the idea is to maximize its use is you want to build a corner reflector. This is a total hacked up version, and there's a lot more work to be done. But basically what you do is you point it, you have 90 degree angle here, and you point it into there, and you have a boom that comes out. And the idea is that signals get reflected from both sides and hit it, and increase the actual gain on that antenna. Now, lastly, the thing that I really wanted to mention is this next bigger project, and this is the last thing. One of my goals is that since all these devices are so cheap now, I really want to have everybody be able to build their own receiving arrays sort of like around the world, and then somehow link them all up in some sort of like worldwide RF sense network. And so that, I mean, it's more locally, you'll see propagation of signals and stuff like that, but it would be interesting to see what the global picture looks like over the whole spectrum. So please email me at ar@watson if you want that source or to help out with this at all. And again, I will be releasing the source soon. So thank you to these people, and remember the Radio Punks list. Sorry this was a little bit rushed, and I'm glad that you guys all got to stay, and sorry if you missed Glenn. Thank you.
Oh. Well, thanks for bearing with us, and
Questions?
enjoy the rest.
Yes. Yeah, it's a good, so there are things that are not discussed in here basically to shorten the talk, which is, thank you. The question was basically, I mentioned earlier about watching the watchers and that political statement, and with the hardware devices that I have now, can I really do what I want to do, you know, say doing 50 megahertz to 2200 megahertz, that kind of thing. Now, you're right, you have very good points there. One thing that I did not mention is the use of you know, up converters and down converters and things of that nature in order to say, you know, do in the L band and all that kind of stuff, or down and low in the ham bands. So that would be better. But again, you're just adding more hardware and more devices, and you're gonna have to get more cabling and things like that. There's a case to be argued is, should one be using USRPs instead of this? Well, they're like at minimum 700, 800 bucks. I don't have that, and then I don't have like a gig-y network at home, you know, to run that. And so, while this may be a bit of a hacked situation, it kind of works. And for the moment, yeah, it's a start. And maybe there's things to do. Maybe instead of buying 4 dongles, you buy one USB thing that does FFTs on the USB stick itself, that kind of thing, and just sort of change it so that there's more specific hardware that's still relatively cheap. Is there any other questions? Yes.
Yeah, do you think one of those low-powered ARM boards like QB board or Raspberry Pi would be sufficient to run a slave node here?
Could you repeat your question, please?
This he was asking whether or not, like, say, Raspberry Pi or some other small form factor, low power device would be able to power one of these. And that's a good question. I don't know very much about how well FFTs work on RPi and that kind of thing. My guess is that it would work. I know people have done spectrum analysis using phones and just the dongle attached that way. So, and actually, now that I'm really thinking about it, I have heard of projects using RPi doing spectrum analysis with RTLT SDRs. So that would work. And this sort of, another thing that I was unable to touch on was I did some work in terms of placing, with friends, laptops throughout the town that I live in. And basically using the public Wi-Fi. And what I would do is I opened a port up on my router and basically did scanning from those places throughout the town, you know, log their latitude, longitude, and then use the public Wi-Fi to send the data back home. And so part of my thinking is that if one had the money, or I'm sure people maybe do, or just have enough hardware to do this, is you could just take one of those RPIs with like a battery pack or maybe some sort of solar thing, throw it in a bush, throw it on like a roof, and then have it talking over the public Wi-Fi back to you, and you're getting data from all around the town. And that way, and that's sort of my real desire, but the costs on that are a little bit prohibitive for me. Okay.
If you have a question, please stand next to your mic. Otherwise, the people on the stream won't get it.
I can address the floating point, like the FFTs on ARM a little bit, because I've been using ARM boards for some robotics, and they work fine if you're going to do it like if your FFT was going to be sort of like a batch process where you're listening and you're gathering data and then you would process it later. They're not, the performance on ARM right now for floating point comparison to Intel is still really not that good. Where it kind of falls down is if you're trying to do something like real-time sensor integration, like through a Kalman filter. BeagleBone Black can do that, but like you would want to have one board dedicated just to that, just to doing your FFTs or just to doing your other floating point operations.
Okay.
I have a robot at home where I'm using a BeagleBone to process data off of a lidar, and just the amount of which is spinning around at like 360 times a second. So that's enough to keep one BeagleBone busy, and then the Kalman filter to integrate the odometry along with the data coming off the IMU to do the sensor fusion pretty much requires another separate unit.
Is it, so we're talking daughter boards? That is feasible,
no,
or?
these are just separate individual units. They're hooked up together over a small Ethernet switch. There's a communicating over XML RPC, publish subscribe protocol. But I had to add a separate board just to do the EKF transforms, because it just, that kind of floating point just crushes a little board like that, and I have a feeling that a Raspberry Pi would be less. So I guess what I'm trying to say is, if you want to do this as sort of like a batch thing, like you go to sleep and you let it run overnight or something like that, would probably be
Gotcha.
okay. It's just not going to be good for real time.
Gotcha, that makes
I
sense.
see people leaving. We're running kind of late, so if you have more questions, please talk to the speaker afterwards.
Thank you.